This is problem number 53 from chapter 5. Two blocks are in contact on a frictionless table. A horizontal force is applied to the larger blocks as shown right here. If this mass is 2.3, this guy is 1.2, and the force is 3.2, we want to find the magnitude of the force between the two blocks. So let's just start there. Whenever I have a problem like this, or really whenever I have any problem, I like to draw a free body diagram if applicable. And so what I'm going to do, since I have two different blocks, is I'm going to draw two different free body diagrams, and then we will choose which one is a better choice with which to sum our forces. So this one is mass 1, and I'll put 2.3 kilograms right in the middle so that we know which one that is. And so, of course, I have my normal force, and I have my weight. But then we have this applied force, and we know that we can put that on this guy because it is literally touching this block. And so that is legit. I will put F for that force. Underneath, I will put that equals 3.2 newtons so that we remember that we actually have the value for that. And then the other force that's going to be applied to this block is the force from M2 onto M1, because as this is pushing along, this little guy is pushing back on him. And so I will draw this force right here. I will label it force from 2 on 1. And so here's our free body diagram. And now I'm going to go ahead and draw the free body diagram for M2. Not to scale, but just big enough that we can see what's going on. So I'll write 1.2 kilograms in the middle of it so we recognize that it's M2. Of course, I have force normal for block 2, weight for block 2. It's always good to indicate that these are different forces from each other. And then in the x direction, I may not draw this force, because this force, although it is affecting ultimately the motion of this, it is not literally touching my block. Therefore, I cannot draw that force on there. The only force that's being applied is the force from M1 onto M2. And so I could draw that right here. Force from 1 on. And we also know that this force should be going in this direction, because since this is the only force in my x direction and we are accelerating in this direction, since our main force is in this direction, that means that this force must be going that way, because otherwise my block wouldn't be moving that way. So here we are, and I have my two different free body diagrams, and this force from 2 on 1 equals the magnitude of force from 1 on 2, because of Newton's third law. These forces are equal and opposite forces. So if we solve for either of these, that will be the answer to our problem. So I'm going to choose this free body diagram because I have only one force here instead of two forces. It's relatively equal. It wouldn't be a wrong choice to choose this one, but I'm just going to choose this because it seems slightly easier because there's less stuff to deal with. So I'm going to sum the forces in the x direction because I don't really care about the up and down force. I just want the x direction. That will equal mass times acceleration. And so the force in the x direction for this free body diagram only, not that one, would be my force from 1 on 2. That equals the mass, which is 1.2, because we were just dealing with this free body diagram, times our acceleration. Now, we obviously have two unknowns right here. We want to solve for this, but we do not yet know our acceleration. And so in a problem like this, I highly suggest drawing a third free body diagram. And this third free body diagram is going to be really useful in solving for acceleration. So my third free body diagram is going to be both of them together. So this will be 2.3 plus 1.2. And here, of course, we have normal force of 1 and 2 together, the weight of 1 and 2 together. These don't matter too much because we're just dealing with the x direction. But then the only force I need to draw in the x direction is this force, F equals 3.2 newtons, because these forces right here are inside our whole system. And so they will cancel each other out, so we don't even need to worry about them, which is great because that gets rid of the unknowns. So summing the forces in the x direction of this whole thing, my only force I have is the 3.2 Newton force. And that equals a mass of 2.3 plus 1.2, because it's the whole mass. You always include whatever mass you're dealing with, times acceleration. So now you see that the only unknown in this problem is our acceleration. So when I solve, I will find out that my acceleration is 0.9143 meters per second squared. Now this is the acceleration of the whole system, which means it's the acceleration of the little block, the acceleration of the big block, the acceleration of everything, because it's moving together as a unit. So now I come back over here, and I know that my force from 1 on 2 equals 1.2 times 0.9143. And so I will find out that the force from 1 on 2, which is the magnitude of the force between the two blocks, equals 1.1 Newton. Awesome. Done with part A. Okay, let's carry on to part B. So for part B, is saying if a force of that same magnitude is applied to the smaller block, but in the opposite direction, then the force between the blocks is going to be something different than what we just got. So no big deal. We can totally deal with this. Let's redraw our free body diagrams, but because they're going to be different. So first I will do the free body diagram of them together. So here's my force, which equals 3.2 newtons. And so I show this because it looks almost exactly the same thing as this, and mathematically it is going to be the same thing as that. I'll show it really quick. So sum of the forces in the x direction equals mass times acceleration, still 3.2, still the same two masses, and therefore my acceleration of the whole thing is still 0.9143 meters per second squared. So our acceleration of the whole thing is exactly the same. But now if I draw my individual, here I'm separating that out, my individual free body diagrams is going to be slightly different. Because see, for our 2.3 kilogram block, now the only force I have in the x direction is a force from 2 on 1. Whereas for my little dude, my 1.2 guy, I have the force from 1 on 2, and also my force, which equals 3.2 newtons. This is my applied force right here. So, and of course, normal force, weight, normal force, weight. If I'm now going to solve for this internal force, I'm now going to choose this one because I only have one force right here, and so it's slightly simpler calculations. By the way, if you chose this one, that's fine. You would just have to use both forces. So sum of the forces in the x equals mass times acceleration. So F from 2 on 1 equals 2.3 times my acceleration, which is still exactly the same thing from the first part. And so that shows us that that force from 2 on 1 indeed does equal 2.1 newtons. And so what they said was true is true. So now let's deal with the third part. Explain the difference. Why is it that when I push from this way, the internal force is smaller, but when I push from this way, my internal force is bigger? And here's the reason. We found out that our acceleration, no matter which way we're going, is exactly the same thing. But if I'm trying to accelerate this little block, so I'm pushing from this way, that requires less force to accelerate this little block, which is what that push is doing. But if I'm trying to push this way, that same acceleration, now I'm trying to accelerate this big block. That requires a bigger force to allow for that same acceleration. I have a little example right here. I don't know if it's actually going to be helpful, but I have a big thing right here and then a little guy right here. So if this little guy needs to push that way to make my weight accelerate, he has to push pretty hard. And so that's the bigger force, the bigger internal force. But for that same acceleration, if this is pushing my little guy, that requires very little force to make him move. So that's kind of what's happening here. You can kind of play around with your own two objects at home and kind of have more of an intuitive feel for it. Hopefully that helps. But yeah, that's it. The end.